All right, it is time to talk about half-life. This is our last topic in nuclear chemistry, and then review. Ready? Okay, so half-life relates to radioactive decay. So any nucleus that is unstable and is going to fall apart and decay is spontaneous, right? So that's natural decay, natural transmutation. It's all listed in table N. And in the process of decaying, it's going to transmutate, change into a different element, release a particle, release gamma radiation, and release a whole lot of energy. This is why nuclear reactions are fantastic in terms of energy. And also remember, mass, a small amount of mass, is converted into energy in a nuclear reaction, which is why we get so much energy from it. So what is half-life? Well, half-life is the amount of time it takes for half of a radioactive isotope to decay. We use time as the unit, so the half-life could be 3.4 seconds, it could be 7.21 hours, or years, or milliseconds, or days, okay? It is specific for each radioisotope, for each nucleus that is radioactive. Important. All of the isotopes that are decaying do not literally decay at the same time. So if the half-life is 5 minutes, all of it is not there, and then all of a sudden at 5 minutes, half is left, okay? It is decaying slowly so that by the time we get to the half-life, half of it has decayed, okay? So on the next slide, we're gonna watch a GIF of radioactive decay. You have a table in your notes, and the first row is done for you, but what I want you to do is record the data that you observe, okay? Remember, you should be writing this down in your table. Watch and write. Halfway there. Okay, you should have all that data recorded. All right, so now we're going to complete the table. So we're going to do the first two half-lives together, make sure you understand what's going on, and then I'm going to leave you, you could work with your table partner to finish it, and then I'll show you the completed thing, okay? So let's look at this and make sure you know what you're doing. So at half-life 1, we had 500 parent isotopes. They're not decayed, they're still left, they're still radioactive. And then the daughter is the one that it decayed into. So it didn't disappear, it changed into something else. So how many total isotopes do we still have? We still have 1,000. 500 are still radioactive, and if not decayed, 500 have decayed into the daughter isotopes. So how much of the parent is undecayed? How much of the parent is left? Well, 50%. All right, now let's look at the next one. We had, for parent isotopes left undecayed, we had 250. And then the daughter, you should have recorded 750. So how many total again? Well, again, this should be the same. So this should be the same all the way down, right? The total number of isotopes shouldn't change. It's either still the radioactive parent or it has decayed into the daughter isotope. Okay, so how much of the parent is left? Well, half of that 50%, 25%. Okay, so I'm going to leave you to finish. So pause if you're doing this and try and finish this up, and the next slide we'll look at it. Okay, so here we go. Here is all of the table filled out. And what I want you to notice is that as we go from 1,000 parents isotopes, after one half-life, we have half of that 1,000. After another half-life, so 2 half-lives have gone past, now we have half of that 500. Another half-life, half of that 250. Another half-life, half of that 125. so on and so on. And the same thing is happening to the percents. We started with 100% parent. After one half-life, we have 50%. After another half-life, we have half of 50, 25%. After another half-life, we have half of 25%, or 12.5%. All right, so we're going to explore half-life a little further. We're going to watch 3 different GIFs. And in your notes, or as you're watching the video, what do you observe? What do you notice? And I want you to think about, write down 2 things that you notice. GIF number 1, watch, observe, pay attention. Notice that, and this, and this. GIF number 2. Notice this, and this, and this. Ready? GIF number 3. Okay. Let's share ideas. What did you notice? We watched 3 different ones. So here was GIF 1, here was GIF 2, and here was GIF 3. Okay? What did we notice? Right? What did we notice was happening? Did you see? Did they all decay at the same rate? No, they did not. Did one decay faster than another? Yes, it did. Which one did decay faster? When the radioactivity was high or when it was low? What do we notice? What do we observe? So radioisotopes with shorter half-lives are just going to decay faster. So this is the same amount of time. But do you see it in the top how much more has decayed because it's decaying faster, even though the same amount of time has passed? So this is important for the usefulness of radioisotopes. So why is iodine-131 useful to diagnose and treat thyroid disorders? Because its half-life is appropriate to be in a human. Okay, it's not lasting for billions of years. Okay, carbon-14 is used to date once living things. Why? Because literally organic chemistry is the backbone of things that are alive. Protein, carbohydrates, everything. Okay, so it's found in living things, first of all, so it's useful. Okay. So why do we use uranium-235 instead to date rocks? Well, first of all, rocks not reliably containing carbon, right? Also, because the half-life of carbon-14, which is, between 5,000 and 6,000 years, let's just say that is too short to date rocks that could be billions of years old. Not enough carbon-14 left to be able to tell how old they are. So uranium-235, which has a very long half-life, is much more useful. Okay. So remember on table N, it shows the specific half-lives of different nuclides. Okay, this is useful and you have to look at it. We looked at it previously for the decay modes and briefly mentioned half-lives, but now we need to use the half-lives. So here's an example. And you have this in your notes using cesium-137. Okay, so the half-life for cesium-137 is 30.2 years. So there's lots of things here that are going to help you moving forward. So what I want you to see is that we're starting with 200 grams, right? No half-lives have passed. It's at time 0. So after one half-life is left, we'll have half of 200, so 100. After another half-life, half of that, then half of that, then half of that, then half of that, okay? You could also be asked the information in terms of fractions. So we're starting with 1 whole, right? So after a half-life, we have half left. Then half of that, which is a 4th, and then half of that, which is an 8th, and then half of that, which is a 16th, and half of that, which is a 32nd, and a 64th, right? And continuing on. You could also be asked about percent. So we start with 100% undecayed, right? We have all of the parent isotope. After one half-life, we have 50% left. After a second half-life, we have half of that, 25%. Another half-life, half of that. Another half-life, half of that. Another half-life, half of that. Okay, so hopefully that makes sense. Now the last column is dealing with the amount of time passed. So remember I told you the half-life was 30.2 years. So in the beginning, no time has passed. After one half-life, when we have half of the amount, half of the fraction, half of the percent, one half-life has passed. And for cesium-137, that specific amount is 30.2 years. Okay. After another 30.2 years, that's when everything else goes down by another half. So each half-life is going to take another 30.2 years. So when I'm at the third half-life, it's taken 90.6 years. Why? 30.2 years for the first half-life, 30.2 years for the second half-life, 30.2 years for the third half-life. Then it's going to take another 30.2 years for the fourth half-life, and then another 30.2 years for the fifth half-life. Okay, so that amount is just continuing, right, showing you how much time has passed. So let's look at an example. So it says, how long does it take for a 20-gram sample of calcium-37 to decay to 2.5 grams? I included right here, this is the row from table N for calcium-37. I included up here the table with the cesium example, all right? But what I like to do is just write a bunch of information down and see what I need. So I'm starting with 20 grams, right? After one half-life, how much would I have? 10 grams, right? After another half-life, how much would I have? 5 grams. After another half-life, how much would I have? 2.5 grams. Oh, look at that, 2.5 grams. Okay, so what happened here? This was my starting point, right? So this is half-life number 1. This is half-life number 2, and this is half-life number 3. So how long does it take, right? So each half-life takes 182 milliseconds, right? So half-life number 1 took 182 milliseconds. Half-life number 2, 182 milliseconds. Half-life number 3, 182 milliseconds. So I could add 182 plus 182 plus 182, or multiply it by 3 to get my answer. So 3 times 2 is 6, right? 24, here are the 2, 5, 46 milliseconds, making sure you're keeping the units correct, okay? All right, another example. So this is nitrogen 16. Here is its half-life, okay? This one is asking about a fraction. So I want to look at fractions. And it doesn't give me a starting mass, which it doesn't have to, but it does give me amount of time. So how much do I start with? 1 whole. Remember, I start with 1 whole. After one half-life, I have a half left. After another half-life, I have a fourth. After another half-life, I have an eighth. Now remember, this stuff isn't disappearing, it's just converting into its daughter isotope. Then I have a 16th. Okay, I'm running out of room. Hopefully that's enough space. So this is half-life number 1. Remember, this is the starting point. So this is half-life number 2, this is half-life number 3, and this is half-life number 4. But I don't know how many half-lives it took. Well, each half-life takes 7.13 seconds. So this one took 7.13. This is how much time passed, right? So 2, it takes another 7.13 seconds. So 7 plus 7 is 14, so I know I don't have enough, okay? Another half-life is another 7.13 seconds. So 7 times 3 is 21, not there yet. And half-life number 4, 7.13 seconds. 7 times 4 is 28, so 7.13 times 4 should be 28.52. Now, if you notice what I could have done, since I know the half-life, right, and I know how much time has passed, I could have taken 28.52 and divided it by 7.13. That would have given me how many half-lives passed. And my answer has to be a fraction. So I had to use all of these, right? So what fraction is left? 1/16. Okay, another example. A 500-gram sample of phosphorus 32 begins to decay. What is the mass of phosphorus 32 when 1/8 of the sample remains undecayed? Whew, so I got a lot going on here. All right, so let's first jot some things down. So 500 grams after one half-life would be how much? 250, right? 250 grams. This is one whole, this is 1/2. I need to get to 1/8, right? So then I'm at 125 grams because half of 250, and I'm at 1/4. Not far enough yet. Sorry, it's a terrible 4. Okay, and then another half-life, I am at what? What is half of 62.5 grams? And that is 1/8. Okay, 1/8 of the sample remains undecayed. Ding, 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 ding. What is the mass of the phosphorus? Oh, 62.5 grams. There we go. Okay. Now you have some work in Schoology. As a half-life puzzle piece, get to it. Show me that you know this stuff.